All right, lecture 24. It's going to be continuing lecture 23 where we introduce the idea of a ring. So we're going to review the definition of a ring and basic examples. We will also look at some basic properties and proofs. And then in lecture 24b, that'll continue more examples, properties, and proofs. And we will also start chapter 13 on integral domains and fields, is what they're called. In the time that we have remaining during the semester, we are probably going to go a little faster than we've been doing, probably about one chapter per lecture starting now. I am going to do, the last half essentially of chapter 12 and the first half of chapter 13, so lectures are going to kind of overlap chapters to some degree. So we're going to go about one chapter per class period until we get to about chapter 20. And definitely chapter 20 we're going to need to slow down. Chapters 20, 21, 22 probably will take a couple lectures each if we do indeed get as far as I'd like to get. Again, that doesn't mean there's going to be more homework than usual. Probably in the neighborhood of 8 completion problems per assignment and 1 or 2 or 3 graded problems. But again, those last couple weeks of class, I'd like to free you from having to do completion problems. And you can just work on the graded problems that I assign, and also I will still make answer keys for other problems that you can just study to help you start get ready for the final exam. All right, so we're going to go pretty quickly over the definitions and basic examples, because that was in the previous lecture, because mostly we're going to focus on the properties and basic proofs. So again, a definition of a ring is that it's a set with 2 binary operations. And we do typically call them addition and multiplication, and that is the most natural thing to do. Not that you couldn't have strange examples where you might define some strange operation that could serve as one of the operations of the ring, but that's not the typical kind of thing to do. The most common kinds of examples are natural kinds of additions and multiplications. It's got properties which, again, the book lists out in a set of 6 symbolic statements. I'm going to describe them verbally. R must be an abelian group with respect to addition. Okay, so the binary operation of addition, under that operation, R, the ring, is an abelian group. And as always with addition, we use 0 for the identity. So 0 is the additive identity in a ring. Multiplication exists as one of the binary operations as well. It's not going to be a group under multiplication. And in fact, again, I'll say this again, I said it in the last one, no ring is a group under multiplication. Some rings are groups under multiplication if you take away 0. But 0 kinds of wrecks things if you keep it in there, as far as making it a group under multiplication. No ring is a group under multiplication. Multiplication does satisfy the associative property. We want that to hold. That's a very natural thing we want to hold. The left and right distributive laws, here's again the left one. A times B plus C is AB plus AC. That's the left distributive law, and then B plus C in parentheses times A on the right is the right distributive law. Both of these should hold, though these are not necessarily equal, because the ring multiplication is not necessarily commutative. Let's come back over here. I added a note from that last lecture 23 here that wasn't there before. Maybe you want to write that down. Note, induction can be used to generalize to the situation where the sum in the parentheses for the distributive law has an arbitrary finite length. Okay, it's not that hard of an induction proof. I could leave it to you. I'm not assigning it, but for example, there would be a left distributive law where you've got n terms inside the sum. You may take it as definitely something that is true. That you can do that. It can be proved from the regular distributive law with induction. Okay? And then there's one for the right distributive law as well. Okay, so that's an extra note that I did not add in the last lecture there. Quick remarks again, rings do not necessarily have to have multiplicative identities. When there is a multiplicative identity, we call it 1. And we call it a unity. Okay? Now it's really easy to get the words unity and unit mixed up. They are related, and in fact I was rewatching my lecture 23 and sometimes I got them mixed up. Okay? Unity means the multiplicative identity. A unit means an element with a multiplicative inverse. There's only one unity, but there could be lots of units. There could be just a few units, there could be a finite number of units, but there could be infinitely many units as well. Unity is the identity, multiplicative, one. Unit is an element with a multiplicative inverse. Even when there is a unity, there's not necessarily units, or at least not necessarily all elements are units. Actually, 1 is a unit, always when it does exist, because 1 times itself is going to be 1. It's its own multiplicative inverse. Multiplication need not be commutative. When it does happen to be commutative, we say it's a commutative ring. Don't say a billion ring. Okay? The tradition is to call it a commutative ring when multiplication is commutative. Question?
So the unity, it's not actually an identity, because what about 0? Like
1 times 0 does end up being 0. Is that your question?
So is it actually still considered an identity, even though it's not a group?
It does act like an identity in the sense that
like
1
it's
times
zero.
anything, by definition, is that anything.
Okay.
And even if the ring is not commutative, this will still be true as well.
Okay.
Or we are defining that to be what, that's really a definition of what a multiplicative identity is. It satisfies this for all elements of the ring.
Okay. So it still can be an identity even though it's not technically a group.
Right. It's the ring is not a group. 0 does not have, never has a multiplicative inverse, for one thing. And there could be plenty of other elements that don't have multiplicative inverses. Plenty of other elements that are not units. Yeah, make sure you stop me if you've got questions, okay? I'd like clarification. Here's a slide that was not in lecture 23. What is our main ultimate emphasis in our study of rings? The study of rings is going to feel pretty different than the study of groups, actually. The main thing we focused on with the study of groups is trying to classify them. Typically, we were focused on finite groups. With rings, it's going to be actually fairly different. Not that we couldn't focus on finite rings, and they will be there, but our main emphasis is going to be on actually infinite rings and studying in particular factorization. Most often in polynomial rings. Rings whose elements are polynomials. That's going to be our main application, so to speak. And factorization is an important application, not just to within math, but also outside of math. In applied mathematics. That'll be our main emphasis. So keep that in mind. We're going to be thinking about polynomial rings a lot, which are infinite rings. They don't have finitely many elements, they have infinitely many. Here's a definition. It's not labeled as a definition in the textbook, but it is in there. Let A and B both belong to a commutative ring R, and suppose A is non-zero. We say that A divides B, or that A is a factor of B, or you could say B is a multiple of A, and write, as with integers, A divides B in this notation. So that vertical line again will say divides. If what? If there exists an element C in R such that B equals A times C. And since we are restricting ourselves here to commutative rings when we talk about this, you could also say B equals C times A. There is a notion, you could generalize this to, of left divides and right divides for non-commutative rings. So you can talk about factorization in non-commutative rings, which there do exist, like rings of matrices are not commutative. Multiplication of matrices is not commutative. So you can talk about what it would mean to left divide and right divide, but we want to keep things as simple as possible. And polynomial rings are commutative. So, at least when the coefficients come from a ring that's commutative. So we're going to talk about this less general notion. So for us, whenever we're talking about divisibility in rings, we are talking about commutative rings. Here's an example. In Z5x, so if you watch lecture 23, this kind of notation should seem a little familiar. That's a ring of polynomials. The elements of this are polynomials. That's denoted by the square brackets and the x inside. This is the coefficient ring. The coefficients of these polynomials come from Z5. The only allowed coefficients are 0, 1, 2, 3, and 4. Or if you let yourself briefly have a bigger coefficient, like say 17, you would mod it by 5. 17 mod 5 would be 2. Right? Divide 17 by 5, get a remainder of 2. As an example calculation, let's go ahead and do this one by hand over here. X plus 3 times x squared plus 4, again, in this polynomial ring, Z5x. Go ahead and FOIL it out. We've got binomials here. X times x squared is x cubed, just like you would usually write. X times 4 is plus 4x. X squared times 3 is plus 3x squared. And then 3 times 4 is 12, but only keep it briefly as a 12. Mod it by 5. Really shouldn't write the 12, but I won't make a big deal of it. 12 mod by 5, you're going to get a remainder of 2. Mod 5, if you want to add that, that's fine, but you don't have to. Keep in mind, as you do it, that you are modding by 5. So, come back to the screen here. That is illustrating that this equation is true in this polynomial ring. And therefore, you could say x plus 3, that polynomial, divides, it's a divide symbol, this polynomial. You could also say the other one, x squared plus 4, divides this polynomial too. Okay? So there's a little hint at our main application. Of course, this is going the easy way. Take an already factored polynomial, multiply it out, and then make a conclusion. It would be harder to start with something like this and know that you could factor it like that in Z5x. That would be harder to do. Well, we might like to get to the point where we can do that as a goal. You might wonder, well, what are the applications of polynomial factorization when you're doing modular arithmetic? Well, there are some. Okay, we'll get there. The next few slides were in the last lecture. Let me go over these very quickly. Again, weird things can happen. Z and Zn are both commutative rings with unity under the expected operations. However, Zn is weird when n is not prime. How so? I made Cayley tables, or I made a mistake there. Multiplication tables, don't call them Cayley tables now, because it's not a group under multiplication. Multiplication tables for Zn when n was 4 and 6, and we saw that weird things would happen. For example, we could get the same element occurring more than once in a given row or a given column. That didn't happen with group Cayley tables. Or we could get what are called zero divisors. For example, 3 times 2 in Z6 is 0. I'm going to go ahead and write mod 6. I can just also write 3 times 2 equals 0 in Z6. So this is a ring, but weird things can happen, like you can multiply 2 non-zero numbers and get 0. You already knew that already, back when we were doing modular arithmetic in chapter 0, that this could happen, but now we're sort of saying this is a weird thing in a sense. These are called zero divisors. Z6 has 0 divisors. Non-zero elements that multiply to 0. That should seem like it might be a bad thing as far as solving polynomial equations. Because when you factor something like this, in classes before this class, you wrote something like this, and you said, okay, if I need to set this equal to 0, maybe I'm doing a calculus problem, and this is a derivative, and you're trying to find the critical points of the original function. That allows you to conclude that x is plus or minus 1. But if you've got 0 divisors, that doesn't have to be the case. Just because the product of two things is 0 doesn't mean one or the other factor is 0. So 0 divisors complicate solving equations. There are rings without unity. Okay? I did say some authors say I want my rings to have unity, but I think it's a good idea to allow rings to not have unity. So that allows you to have things like this set to be a ring. For example, if n is 2, this would be the set of all even numbers. It is closed under addition and multiplication. It does satisfy the associative law for multiplication. It satisfies distributive law. It's a group under addition. I'd like that to be a ring. And so with our book and with me, this will be a ring. But it's a ring without unity. One is not in there. There's no additive identity. Excuse me, multiplicative identity. However, the multiplicative identity doesn't have to be the number 1, like in this ring here. 6 is actually the multiplicative identity in there. Which, again, makes you scratch your head and say, well, shouldn't that maybe be a subring of Z10? We're doing arithmetic mod 10 here. Shouldn't it be a subring of Z10 if there is an idea of a subring, and there is? And doesn't Z10 have a unity, 1? Yes. But again, weird things are happening here. 6 does act like an identity, for example, on the number 2, mod 10. But it doesn't act like an identity on the number 3, mod 10. This would be 8, mod 10. It's only one that acts like a multiplicative identity on all the elements of Z10. But one's not part of the set. 6 is acting like a multiplicative identity with these elements. So this ends up being a group, or excuse me, a ring with unity. Amazingly enough, okay? Note the last 2 examples are subrings of the appropriate ring from the first set of the examples. Subsets of the original rings that are also rings under the same operation. Rings of matrices are quote-unquote weird in the sense that they're not commutative. Okay, maybe that's not that weird because we've had non-abelian groups. But just know, rings whose elements are matrices do form non-commutative rings, at least if they're certain kinds of matrices. These are matrices whose entries are all integers. 2 by 2 matrices whose entries are all integers. The usual operations mean usual matrix addition and multiplication. If you allow the entries to only be even integers, then it turns out to be also a ring. It's a non-commutative ring without unity. The identity matrix is not in there. And there is no other matrix that acts as the identity. You could allow the entries to be just from Z2, for example. And this would be a finite ring. This ring would have 16 elements. You've got 2 by 2 matrices, 2 choices for each of the entries, 2 to the 4th, 16 elements for that. There are finite rings, though they're not our main thing of study. Although again, Zn is a finite ring as well. Polynomial rings. Again, this notation is standard. Zx stands for the set of all polynomials. The fact that they are polynomials is emphasized by the square brackets around the x. The coefficients are integers. They're from Z. That is a ring, a commutative ring with unity. The unity is the polynomial 1. And the additive identity is the polynomial 0. Thought of as polynomials. Now, we're not really being real precise about what a polynomial is. I mean, you know, you ask a high schooler who's taking algebra, is this a polynomial or not? They should be able to answer the question. But we're really not precisely defining it. I mean, yeah, I mean, is this a polynomial or a number? When we think of it as a number, we say it's a number. When we think of it as a polynomial, we say it's a polynomial. What's the distinction? That's not so clear, okay? Polynomials are most typically thought of as functions. And so when you say a number is a polynomial, typically you're saying it's a constant function. If you graph it, it's graphed as a horizontal line. But initially here, we're not really thinking about plugging numbers in. We're not thinking about making graphs. We will later. We're just thinking of these as algebraic objects that can be added and multiplied in the usual way. You can restrict your coefficients again to something else. We did z. What did we do with that other example? z5. Here it's z2. Coefficients can only be zeros and ones. Don't be confused here. This is an infinite ring. For example, x is in it, x squared is in it, x cubed is in it, x to the fourth is in it, etc. X to the millionth power is in it. It's an infinite ring. The coefficients, though, can only be zeros or ones. It does have an interesting property that even though it's infinite, every non-zero element has finite additive order. You add any element to itself, mod 2, you're going to get 0. Because you're doing mod 2 arithmetic with coefficients. And that's got a special terminology that goes with it. It's called the characteristic 2 ring because of that. We'll define the idea of characteristic next Monday. This is a ring called the Gaussian integers. It's a subring of the complex numbers. By the way, the rationals form a ring, the reals form a ring, the complexes form a ring under ordinary addition and multiplication. Very special rings, those are. Not too weird. Zi is the set of all complex numbers of the form a plus bi, I squared is -1, where a and b are integers. So if you know about something called the complex plane, oops. It's a way to imagine complex numbers, to visualize them. You've got something called a real axis and an imaginary axis. An arbitrary complex number, a plus bi, where a and b are arbitrary real numbers, can be represented, can be visualized as a point whose coordinates are a and b. You imagine this point as being that complex number. Well, the Gaussian integers then can be visualized as those points in this complex plane whose real and imaginary parts, first and second coordinates, are integers. Be like a lattice of points. All the coordinates of these points have to be integers. And this goes on forever. Up and down and left and right. That would be a way to visualize the Gaussian integers. And it is a subring of the ring of complex numbers. And I did mention this before, I'll mention it again. The square bracket notation, that kind of is similar to the rings of polynomials, except now it's an I in there instead of an X. And instead of X being an indeterminate symbol that we don't really give much meaning to, except as a placeholder, I does have some meaning. Its square is -1. But this does turn out to be consistent with the other notation, because you can also think of this as the ring of all polynomials in I. A plus bi plus ci squared plus di cubed plus ei to the fourth, for example, would be an element of this, because the fact that I squared is -1 means you can replace that with a -1. That also means I cubed is -I, and it also means I to the fourth is actually +1. And that allows you to simplify this. It would simplify down to having a real part of a minus c plus e. And the imaginary part is what goes next to the I. That would be, looks like, b minus d. times I. So you can simplify factors. But you could think of these as being polynomials in I, where I is the imaginary unit. So it is still consistent notation. Another example is the rationals with the square root of 2 adjoined. This is the standard symbol for that. And here, notice we are using parentheses rather than square brackets. Though we're defining it in kind of a similar way. I'm not going to say why we use the parentheses here instead of square brackets. Actually, there is one spot in your book where the author used square brackets, and then it's kind of consistent with this. But more typically, we use parentheses. I'm not going to explain the distinction at the moment. This is the set of all real numbers of the form a plus b square root of 2, where a and b are rational. So a and b are rational, but you do have an irrational number in this expression, square root of 2, which you should know is irrational. You should know the proof of that too. By the way, it's one of the most beautiful proofs in math. The square root of 2 is not a rational number. That's something you should look up and watch somebody give a 5 to 10 minute proof on that. It's very beautiful. Anyway, in general, these are not rational because you've got the square root of 2 there. But this does end up forming a ring. In fact, it's a very nice ring. Every non-zero element of this actually ends up being a unit. Okay? It's a very nice ring in that sense. And it's important for the theory of solving equations. We will see. All right, on to some new stuff for the quiz here. This is a list of properties in the book. These are fundamental properties, really simple looking, page 229. We just go ahead and write them all, show you all of them right away here. Let A, B, C belong to a ring R. You look at these properties and you say, yeah, those should be true, I would think. Unless a ring is really weird. Well, it turns out even in weird rings, this is still true. Any element times the additive identity is the additive identity. 0 does act like 0 with respect to multiplication. It's not something we assume in the definition because we can prove it. If you can prove something, don't assume it. If you don't need to assume it, don't. This is a theorem. How would you describe this kind of equation verbally? You'd say, listen carefully, A times the additive inverse of B does equal the additive inverse of A times B, which also equals the additive inverse of A times B. Definitely an equation you would hope would be true, and it is true, even in weird rings. R is an arbitrary ring. The book proves it 1 and 2. Let's look at 3. Negative A times negative B. Oh, okay, I said negative, as for short. Really, I should say the additive inverse of A times the additive inverse for B. Right? We're going to talk additive inverses there when we put a negative sign in front of it. Is A times B. What's the quickest proof of 3? I'll let you study the book's proofs of 1 and 2. The quickest proof of 3 would be to maybe to use 2 a couple times perhaps, because we got 2 negative signs here. Negative A times negative B. I'll go ahead and say negative for short, but really, I won't mark you wrong if you say negative either. But really, I should say additive inverse. Additive inverse of A, additive inverse of B, multiplied together. By property 2, first applied with the negative sign, well, I guess I could do both at once. No, let's do one at a time. Let's think of an arbitrary element times the additive inverse of B as being that. So what does that mean here? I'm treating the negative A as the A up there. This would say I get that. Got to be careful, it's tricky. So I'm using the equality between these two things, but replacing the A with negative A, the additive inverse of A. See how that goes? Now I'm going to use the equality between these two things straight away inside the outer parentheses here. Like that. So I've used property 2 twice. It's tricky. Can I just say this is equal to A times B? Do I need another property? You can just say it's equal to A times B. Why? Because this is really a property of groups. The additive inverse of the additive inverse of AB is a group property. We are talking about addition, additive inverses. In the abstract theory of groups, we wrote that property like this, with powers. We are talking about a group under addition. The additive form of this would be this. That's what I used in this last equality. It is a group under addition. It's tricky. Be able to do this kind of thing and give quick reasons. Say property 4 here now. A times B minus C. There really is a third binary operation going on with rings here, isn't there? Subtraction. Well, what is subtraction? It's really adding the additive inverse. That's what subtraction is. It's defined in terms of addition. And now I can use the ordinary distributive property and write this. And now I can use property 2 again. To say A times the additive inverse of C is, well, we write it like this first. The additive inverse of A times C. But by definition, adding additive inverse is subtracting. Just got to be really careful, think really carefully, clearly about concepts here. If R has a unity 1, then the additive inverse of 1, negative 1, times an arbitrary element is the additive inverse of that element. And in particular, if that element is negative 1, 6 follows easily from 5. If that element is negative 1, then you get the additive inverse of negative 1, which is 1. 6 follows easily from 5. Why is 5 true? I'm claiming this thing is the additive inverse of A. So if I add it to A, I should get 0. Here's the trick. Write A as 1 times A, which by definition I can do for any A because 1 is the identity. And then use the distributive property, the right distributive property here. I'm not assuming R is commutative. But I can use the right distributive property to say this, and 1 plus negative 1 is 0. And by property 1, 0A is 0. So this implies that that negative 1A is the additive inverse of A. It is a group under addition. All right, let's take the quiz.